In this video, we're going to be talking about a couple things that go along with the pressure controls and thermostat section in your course. I want to talk about the schematic of the day, but I also first want to talk about some of the labs that we've asked for on day 9. You have a lab 9A, 9B, and 9C. So let's take a look at lab 9A. Okay, the whole purpose of this lab is that you can have your trainer wired so the evaporator and condensing unit is controlled by the thermostat. Okay, normally in commercial equipment the evaporator fan stays running all the time. So what this is doing is this is downgrading, well, basically altering the operation of a commercial piece of equipment on your trainer board to be that of a smaller reach-in cooler, one perhaps that's under a counter someplace or something like that, that the fans actually only run when the system is calling for cooling. Okay, you're going to draw a ladder schematic of that. Okay, you're going to wire it, and it doesn't tell you anything about what types of motors. Just take a look at your training unit. Your evaporator fan section has shaded pole motors. Your condensing unit has your condenser fan is a shaded pole, and your compressor is a CSIR motor. So you're going to have two EFM motors on most of your units, okay, that are in parallel. You're going to have a condenser fan that's in parallel with your compressor. Those will cycle on and off together. Okay, have it checked out, wire it, give a good sequence of operation. Okay, what happens when you're calling for cooling, what happens when you're done calling for cooling. The questions go along with motors. Okay, the current draw on the motor at startup is known as locked rotor amps. The condenser fan motor winding, okay, it's grounded. Okay, if it's grounded, it's going to trip the circuit breaker because, again, a direct short to ground is going to trip the breaker. Alternating frequency goes back to our basic electrical, 60 hertz. The start windings always have more turns than the run windings. That's why we have to take the start windings out of the circuit once the motor started. Typical split phase motor reaches approximately 75% of its operating speed. Okay, this is a split phase. It's normally opened by a centrifugal switch. What's the one thing you should never do with an ohm meter? Use it on a powered circuit. And if you read 120 volts across a switch, it's open. Because remember, voltage across a closed switch is 0. Voltage across an open switch is source. Okay, two ways to determine a bad motor using an ohm meter. One, if you have an open winding, in other words, you're measuring from start to common or run to common, and if you get OL, you have an open. The other is checking from any one of the leads to ground to the motor frame. If you have any type of resistance from any lead of the motor to the frame, you have a shorted motor. Okay, and you can have any place from, you can have resistance that are in the mega ohms. It won't cause damage. You can still use the motor, but once you start getting down into the kilo ohms and the ohms, you really need to replace that motor. The drawing here is for the circuit. Again, you have a thermostat that controls both your condenser, which has a condenser fan motor and a compressor, and your evaporator. Please make sure you actually label things properly in that lab. Now, lab 9B, okay, you're basically adding to the circuit in 9A. So once you have your circuit in 9A, what you're now doing is you're adding, okay, low pressure, high pressure control. Okay, so the low pressure and high pressure control will control the condensing unit, does not control the evaporator fan motors. Okay, the evaporator fan motor is being controlled by the thermostat along with the condenser, but in series with the condensing unit, you're going to put your low-high pressure control, because what we really want that to do is to kick off the compressor. Okay, so it's a dual pressure control. It has a high and low pressure control right inside of it, so use the proper symbols on that. Okay, what type of capacitors on your compressor? All of the units in the shops have a start capacitor on it. Sort of a trick question here on B. What drops this out of the start winding on a PSC motor? PSC motor, the start winding stays in the circuit. Permanent split capacitor, that uses a run cap. What's the purpose of the run capacitor? It changes the phase of the current a little bit that's hitting the start winding. So it makes the AC current a little bit out of phase, and therefore it adds to the running efficiency of the motor. The microfarad range for run capacitors and start capacitors, 5 to 60 is your run capacitor, and 60 on up is your start capacitor. Remember, run capacitors most often have a metal case. Start capacitors have a plastic case. What happens to the capacitor on your compressor once the motor reaches approximately 90 or 75% of the rated RPMs? The start capacitor drops out. The run capacitor stays in the circuit. Okay, so anytime you have a start capacitor, you also have a starting relay, some sort of relay or start component that will take that capacitor out of the circuit. Okay, we're asking you to draw a schematic of a CSI fan motor. In yesterday's schematic of the day, you actually did one of these. CSIR, capacitor start induction run. It has to have a start component. Draw a schematic of a CSCR motor on the next page. CSCR will have two capacitors, one a start capacitor that's taken out of the circuit, and one a run capacitor. A hint for this one, the easiest start component to use on this is the potential relay. On this one, the easiest component to use for this is going to be your current coil relay. And there's plenty of space for drawing, okay? So that's 9C. 9C, okay? You are going to use the low pressure control, okay, to control the system. Now, on this one, what I would do is take your circuit from 9B, the one you did on the last one, and I would just take the thermostat out of the circuit. Okay, so you already have a circuit with a thermostat controlling the entire system and a pressure control controlling the condensing unit. What I would do here is just take the thermostat out of the system. Okay, let the pressure control control the condensing unit. And on this one, you want to let the evaporator fans run constantly. Okay, so you're just going to make a change. For the same circuit from 9C or 9B, just take the thermostat out. Okay, have your instructor check your schematic once you've drawn it. Have your instructor check the wiring. Sequence of operation include the pressures, and you want to use your gauges on this one. Okay, what's the purpose of a centrifugal switch? Back to our motor lecture. Okay, the centrifugal switch takes the start winding out of the circuit for a split phase motor at about 75% of the rated RPMs. What's the difference between a run capacitor and a start capacitor? Microfarads, the amount of kick the capacitor can give. Run capacitor is 5 to 60, start capacitor is 60 on up. Okay, also run capacitors most often are metal case, start capacitors are plastic. What's the run capacitor filled with and why? And I'll let you look that up. Okay, there's a couple different answers. Which winding is a run capacitor wired in series with? Capacitors are always wired in series with the start winding, never with the run winding. It's sort of misleading on what they're called, but a run capacitor is always wired in series with the start winding, and it's in parallel with the run winding. Describe how low pressure switch operates. Basically, the pressure in the refrigerant on the low side drops below the set point. the low pressure switch opens until the pressure in the refrigerant low side returns to the cut in. High pressure switch is on the high side of the system, usually discharge side of the compressor. Okay, the pressure in the system exceeds the high pressure cutout. Okay, the pressure switch will open. Most often, high pressure switches are a manual reset unless they are being used as a condenser fan cycling. Draw a symbol for run capacitor. It's a capacitor. Okay, you can put a dot next to the one with the run capacitor as well, but you don't have to. Just label it run cap or RC. Okay, and there's place for drawing for your schematic. Now, let's go ahead and take a look at the schematic of the day for number 9. So, what we're looking for is draw the following list of components for proper operation. All starting relays must be represented along with motor windings and other needed components. All must be fully labeled. Use start relays instead of centrifugal switches. EFM 1 and EFM 2 run all the time. So we know we have a cooling thermostat. Okay, we have a split phase 120 volt motor. We have a PSC motor, 120 volt. We have our condenser fan motors. We have a CSIR, a CSR. Now those are 240 volts, okay? So most likely what we have here is a split system. We have an indoor system that's 120 volts. We have an outdoor that's 240 volts. Okay, so just be aware of that. We have a CMP, a compressor 1, 240, compressor 2, 240. Okay, so what we have is we have 2 EFM motors and inside in a cooling thermostat. We have an outdoor unit with CFM1, CFM2. Okay, now, this schematic is going to get a little strange. You have an option here. We could throw a contactor in here, which we might actually do to cycle the outside unit and use 2 different power supplies, or you can run part of the 240 volt circuit outside. I am not a fan of that. I like having 2 feeds, so that's probably what we're going to do in this case. So let's start off with the indoor part of this, okay? So I'm going to come over here, okay, and I'm going to label this the indoor portion, okay, and it's 120 volts, and I'm going to put that right there. Then I'm going to come down, because it's 120, I'm going to have an L and an N. Okay, now we're going to move that, I think, a little bit. Okay, so let's go ahead and give ourselves a little bit more room. Okay, we know that every single circuit we deal with, okay, we're going to have a service switch. So let's go ahead and just give ourselves that. Okay, I know I'm going to come out here with my neutral. Okay, let's go ahead and give our service switch. We're going to go ahead and label that service switch. Okay, now, I want to go ahead. The first thing I'm going to do is I'm going to come out and let's give ourselves our thermostat, because we've already been told everything is going to be controlled by the thermostat for the outside unit. So let's not forget about that thermostat. It's a cooling thermostat. Okay, I'm going to go ahead and freehand in my thermostat symbol. Okay, then out of my thermostat, let's go ahead and put in, and let's make it so that I can actually read it. Yeah, sometimes we just don't do well with our drawings. Let's put in our coil. And let's go ahead and label that CC. And let's go ahead and come here and label that TS for thermostat. Okay, so now we've taken care of at least operating the outdoor system. So the other thing now I want to do is I want to come in and let's go ahead and draw in for our motors. Okay, I got to give myself enough room for the motor. So let's, our first motor, if we take a look back at the diagram, split phase, 120 volts. Okay, so let's go ahead and we're going to give this, we'll give this a current coil relay. What do you say? Okay, so we'll label this. This is my run, start, common. We know we have a main. We have S. And we have L. Okay, and we're going to just go ahead and label this. Let's put the label right there, EFM1. Okay, so I have my 120 volt evaporator fan 1. Now, let's go ahead and we're going to go ahead and draw in my evaporator fan 2. This one is easy. This is a PSC motor. No start component needed, because all I have in here is my run cap. And we're going to go ahead and just feed it with power from there. Okay, let's go ahead and label that. I'm going to say EFM2. And let's label that common. Okay, so that's my indoor portion. Okay, so this becomes really easy. Okay, we now have my indoor. Now, my outdoor is a different story, because we now have 240 volts. So let's go ahead and label the outdoor unit and make sure it's classified as 240 volts. Okay, I'm going to give myself lots of room on this one, but I'm going to use an L1 there, and I'm going to use an L2. There, we have a line 1 and a line 2. I'm going to go ahead and, first of all, move that one up. And I'm going to put my ladder in first, okay? So again, I want to put my rails in for my ladder diagram. So what I'm going to do is basically come in here, and I'm going to give myself, again, plenty of room on this one. Okay, I'm going to then come there, and I'm going to give myself plenty of room. Now the other thing that I'm going to do is I'm going to shorten this one a little bit. I'm going to shorten this one a little bit. And I'm going to come in and draw there, there, and I'm going to put in my circuit breaker. Okay, this is pretty important. So I'm going to, again, I want to label, we're just going to say SS1 and SS1. Because every unit has to have a power disconnect on it someplace. Okay, so now what do we have outdoor? Okay, it's asking for us for 2 compressors and 2 condenser fans. Okay, one of the compressors and one of the condenser fans is a CSIR, capacitor start induction run. So now the other thing that we noticed is the outdoor unit, okay, actually has, remember, it's controlled by that CC, the compressor contactor. So we're going to just make another small change on our wiring here on both sides, okay, because I want to control that power. So I'm going to come out of that service switch, and I'm going to go to a normally open contact first. Okay, I'm going to label that CC on both sides. Now, what that does, okay, remember the CC up here that's being controlled by my thermostat? Okay, that's controlled, that's connected electronically to the outdoor CC. So this is a 120 volt coil controlling a 240 volt load. So let's go ahead and I'm going to draw my first motor. Okay, and I'm going to draw it pretty far over here because I want to give myself lots of room. Okay. So, and I'm also going to go ahead and draw in that second, I'm going to do both CSIRs at the same time. Okay, so if we take a look at here, I have a CSIR condenser fan, a CSIR compressor. Okay, CSIR is capacitor start induction run. So on both of these, what I need to do is have a start cap that's taken out by some sort of relay. So in this case, I'm going to go ahead and use my current coil relay, which basically has my my current coil relay has an open contact that closes when it reaches the high current of the LRA and energizes that start cap. Okay, and I'm going to do the same thing down here. I'm going to go ahead and use a current coil relay, okay, that has a normally open contact, comes down, and energizes my start cap. And I really don't like the way that start cap's drawn, so we'll redraw that. Okay, now I'm going to go ahead and connect in my common or my line 2 for both motors. I'm going to connect in my run for both motors. And try to neaten it up a little bit. I want to label everything at this point. So this is my L, L, M, and we might as well throw the run in there. And we'll put my S, S, C, C, mark that as start cap, mark that as start cap. Okay, and this is my EFM1. And this is that's my comp one. Actually, that is CFM1. So let's fix that. Okay. So now if we look at our diagram, I have compressor 1 out of the way, I have CFM1 out of the way. Compressor 2 and CFM2 are both CSCR motors. Okay, let's go ahead and I'm going to go ahead and we'll draw one here. So again, I'm going to draw my motor first. Okay, CSCR motors we start off with a start cap or run cap. Remember, it has a permanent capacitor in it. Okay, so we have that. Okay, then I have to have some sort of starting component. In this case, I'm going to go ahead and use my potential relay with pins 1, 2, and 5. Okay, and that's a normally closed. Okay, pin 5 connects to common. Pin 2 connects to start. And then what we do is we have a start cap that connects there. Now what I'll do is in this case, I'm going to go ahead and label next. That's an SC. Might as well get the run cap while I'm there. That's my run winding. Start. Common. And I'll get that taken care of. Okay, so I have run, common, start, pin 1, 2, and 5. I have my start capacitor. I have my run capacitor. Okay, I'm going to cheat a little bit. And I'm going to copy that. And I'm going to basically edit, copy. And I'm going to well, I want to undo that. I got it to the wrong place. Let's go ahead and I'm going to edit, paste that in. Okay, so this is my CFM1 here, or my CFM2. This is my compressor 2. Let's go ahead and wire that in. Okay, and let's label this so we don't lose track of where we're at. 2 and okay. So looking back at our circuit, what we have our indoor unit with an EFM1 that's a split phase, outdoor, or again EFM2 is a PSC. We have that running constantly. We have a TS that's controlling my compressor contactor or my condenser contactor. Outside is a 240 volt. I have a CFM1, a CFM2. I have a Comp 1 and a Comp 2. Okay, they're different types of motors. None are controlled by a centrifugal switch. So if we look back at our circuit, what we've basically asked for, okay, I have met the requirements of this by this. Of course, my motors could be a little bit neater, but again, I understand that drawing on a tablet is sometimes difficult, so we will leave it at that. Okay, so hopefully that helps out a little bit with these labs.